Today's colloquium, it's my pleasure to welcome Camille Avestruz, who is KICP postdoctoral fellow, but she's also a provost postdoctoral fellow here at the university. So she has wider university-wide affiliation in addition to the local affiliation at the Camille Institute and also at the Institute. Camille is our academic grandchild. I don't know how many people recognize that. She did her PhD with our former graduate student, at Yale University, working, if you know Daisky, you probably can guess what she's been working on this year. It's Galaxy cluster, because when I first saw Daisky here in 2001, I asked him what they're interested in. He said clusters. And he's still at it 16 years later. Camille's thesis was on the outskirts, studying outskirts of galaxy clusters and what they can tell us about the processes that lead to relaxation of gas plasma to galaxy clusters. She won a number of fellowships for her graduate work, and she won a Best Crown Award from AAS for dissertation, which is awarded for outstanding minority graduate students for the dissertation research. Since the last 3 years, she's been here as a KICP fellow, and her interests started to widen, and in particular, she became more interested in machine learning techniques. She's teaching a class right now, a graduate class in this, and she's also applied it in a research project identifying gravitational lenses in the future surveys using these techniques, which is what she'll tell us about today. Welcome.
Thank you for that introduction, Andre. All right, so today I'm going to be giving an overview of both a mock lensing data set in addition to an automated pipeline that we sort of put together in order to test the data set. Hopefully that will help. Okay, so the name of this talk is Automated Lensing Learner, or ALL, because ideally we'd like to find all of the strong lenses that we can in the observable universe. This work was done in collaboration with a number of people, including Nan Lee, who was up until I think just this past month an associate at KICP, postdoctoral fellow, and a postdoctoral fellow at Argonne. So the two images you see right here are sort of maybe encapsulate the ideas behind this work. So on the left-hand side is what you will come up with in a Google image search of just the words machine learning. And the idea behind this is you want to be able to automate the kinds of statistical analysis you might be able to do if you have a very particularly large data set. And on the right-hand side, this is a sample image of one of our mock HST strong lensing systems. So going back to the Google search, I'm going to start off this talk the way I typically start out most of my research projects, with basically a Google search. And basically wanted to see how other people had defined machine learning in the broader community. So from the perspective of a programmer, they define this as a field that is concerned with the question of how to construct computer programs that improve with experience. And in my opinion, it's a little bit of a wordier version of what I would consider machine learning to be, so I kept looking. Here's a very short description of what machine learning might be: learning from data. And that's from the perspective of a statistician. Finally, my favorite is pattern recognition. That's from the perspective of an engineer. And in my opinion, and the way I like to basically view machine learning is that it's pretty much pattern recognition based off of very large data sets. And the approach to which we basically have taken applying machine learning to astronomy and astrophysics is very much the way you want to approach most engineering problems. You start simple, you understand your problem better, and then you build on top of that. So pattern recognition, though, the reason I like that description is because it's kind of inherent to what we do in astronomy and astrophysics in general. So pattern recognition is inherent to astronomy, but in addition to having physical insight, I think that's the key difference between perhaps just flat-out engineering and doing something in the physical sciences. You're also incorporating physical insight. And this comes in a number of applications. For instance, in planetary science, where you might look at some time variability in order to figure out what's physically going on in a planetary system that's orbiting a host star. This pattern recognition and physical insight is also inherent in people who do the theory behind stars, and you can categorize stars basically looking at what's known as an HR diagram. This is sort of another kind of pattern recognition where there's some underlying physical process that determines what area of classification these stars might lie in. And finally, another example is in galaxies, where you might see some sort of pattern between the black hole mass and the galaxy mass of the galaxy hosting that black hole. So you can see there are just a number of ways we can look at a variety of physical systems, everything from the tiniest, right, so may not be tiniest, but so planetary systems all the way down to galaxy systems, and even beyond that, galaxy clusters and the broader, large-scale structure of our universe. So with that, it's not just that astronomy is fairly pattern recognition plus physical intuition based in this regime of things. Well, astronomy is actually fairly data-driven. So this is motivation to really seeking out patterns. So what I'm showing here is kind of a meta-analysis that I pulled off the internet, where basically someone had gone and scraped all of the abstracts from a number of science-related fields. You can sort of see there's a bunch of things including imaging, astronomy is in there, statistics, bioinformatics, etc. And the color coding associated with each of these fields, from blue to red, is basically the percentage of publications that has the word data in the title or abstract. So for meta-analysis, okay, maybe that's like a very rough definition for what you might say is data-driven, but it's to zero order, not so bad. But what you'll notice is that astronomy is in the orange to turning red region of percent of publications with data in the title and or abstract. So what this indicates to me is that of all of these STEM-related quantitative fields, astronomy is becoming one of the more data-driven amongst them. And another indication of this is basically when we look to the future with LSST and Euclid. And these are just two snapshots of the front websites of both LSST and Euclid. So LSST, many of us here are probably involved with, and Euclid is basically the European counterpart to that in a sense. But what I would like to draw your attention to is just this detail, this square box right here, where basically it quotes that 37 billion stars and galaxies, 10 million alerts, thousands of pairs of exposures, and 15 terabytes of data will be taken every night. And what this essentially tells you is that with upcoming surveys, we're going to have a huge amount of data. And with a large amount of data, that basically indicates that we're going to have to figure out how to mine through this data, how to automate a lot of things we might have done manually in order to actually get some useful information out of it. So when something is hugely data-driven, that typically implies that perhaps there might be a useful machine learning application within that data set. So going through some example machine learning applications, probably the simplest form is what's known as supervised classification. So here's just an example pulled from, again, Google, where basically we have a sample of cats and dogs from an online data set. And Google is basically able to automatically see an image of a dog or cat and automatically classify it as either a dog or a cat. And it does this because it already has a set of known labeled images that contain cats and dogs, and it's basically trained some sort of a model classifier to recognize features that are characteristics of either dogs or cats. So you might think of cats as typically having pointy ears. So if Google comes across an image that kind of looks like this four-legged, furry friend that might be in a household, but it has pointy ears, it's going to more heavily weight it towards being a cat than a dog. So it's basically doing this classification based off of pre-labeled data it already has. Another example of classification is known as clustering or unsupervised classification, and this happens when you don't have labels in your data, and you're basically looking for structures in your data set in order to assign these groups. So here's just an example where you might have the height and weight of a variety of people that you want to buy a bunch of t-shirts for, and within this you can basically figure out that, okay, well there's roughly 3 sets of clusters that can go in from small, medium, and large. And then within that, you have categories of t-shirt sizing. What falls out from unsupervised classification or clustering is what's known as anomaly detection. So if you already have some known clusters, some known natural groupings of things according to some criteria, right? In the previous thing, it was like t-shirt sizes having to do with heights and weights. Here it's basically looking at materials having to do with vibration and heat of the material. And you have this natural cluster of red data points. If you have another set of observations of data points and one of them lies inside, you know it's within that cluster. But if something is anomalously outside, you can detect that in a process known as anomaly detection. And finally, just another example that I'm going to talk through is called dimensionality reduction. Now this is something that you oftentimes do if you want to either find patterns in the data that are not visually or easily noticeable, or if you want to basically start to tease out patterns in the data that aren't naturally occurring in the dimensions that they already sit in. So the example given here, mostly just a cartoon setting, is let's say you have a bunch of data points whose continuous distribution lies in what's a 2-dimensional manifold embedded in a 3D space. And here are the sample data points, color-coded by, say, some other attribute. Well, if you were to just project this onto one of the natural axes, you're not going to see that the data points actually naturally separate out in their 2D set space. So what you can do is you can use various techniques to find the curve along which the data that it's most closely related to lie on, and unfold this manifold so you can clearly see the different attributes as they span from, say, red to purple. So these are a variety of things that you can do with existing tools. So the fact that these things exist, that these are potential ways you can use your data to learn other things, basically in terms of pattern recognition, you might ask, well, where does this leave astronomers? Well, to give you some examples of what we've done in astronomy, there is, in the regime of supervised classification, there's been a lot of human efforts done, particularly in citizen science, where humans would actually classify galaxies and their morphologies by eye. This has also been done in the context of gravitational strong lensing, where the human eye is naturally good at picking out these elongated features. So when it comes to image space, the human eye is actually one of the best discriminators of features that make either morphology something that we can classify an object by, or elongated features such as strong arcs characteristic of strong lenses. So this whole human identification has been basically collated into a series of projects, citizen science projects, known as the Zooniverse. For galaxies, Galaxy has been the one that's existed the longest, where basically you can, as a general citizen, click on Begin Classifying and actually start to classify galaxies. In the strong lensing, there exists space warps, where these sites are not only really great in terms of allowing us to now label data according to what humans can identify, but it's also a really great educational tool. There's a link right here that says Learn About Lenses. But I mentioned to you before that one of the things that's coming in time is that, well, we're going to have orders of magnitude more objects to identify and classify as we start collecting LSST data and Euclid data. So what this says is that instead of having to do this by eye, instead of having to do this by citizen science, it's going to scale much better if we can just automatically classify these by, say, using machine learning algorithms. And in fact, classification by automation has been monetarily funded, right? So this is just a snapshot of the Camille competition a handful of years ago, 3 years ago actually, where they basically put out a grand prize of $16,000 to the person who could write a machine learning algorithm that could automatically classify previously labeled galaxies from Galaxy Zoo to the best performance. And what this tells us is, okay, that the field is moving to a point where automation is very much going to be crucial in our ability to move forward and make more scientific discovery.
There's one
Yes, this was won by someone who's now, I think, in data science. He got, not Endora, one of the, anyway, he's not an astronomer, he's a computer scientist who basically got the top prize. So what this also tells us, actually that brings me to another point, is that this is sort of an area where we're going to have to pull in a lot of domain expertise, not just from within astronomy, but also, say, from computer science and statistics. So, where does that leave astronomers, though, if there's this need for extension within the domain of expertise? Well, there is an existing large set of libraries already existing pre-written code that has been tested in a variety of applications that we can also use within our own data sets if our data sets are large enough. And in particular, basically everything that's been used in this talk that I'll be showing you is all from either scikit-learn or skimage. So these are basically Python libraries that allow you to do analysis on large data sets using existing machine learning tools, and also for the image processing part, things that a lot of people in computer vision might have used as well. So just to give you an outline for the rest of my talk, I've just gone through a broad introduction to machine learning and astronomy. And the remainder of my talk, I'll basically just be talking through a case study where I will describe a pipeline for supervised classification for strong lenses, exhibiting a feature extractor and also model classifier. I'll show you some mock observations for testing these methods, show you the results, and I'll leave you with some summarizing remarks. So the context of which we're basically testing this machine learning pipeline is within strong lensing systems. And just a recap, basically you have in your foreground some sort of a massive object, say a massive elliptical galaxy or a massive galaxy cluster. And in the background, you might have, say, a background galaxy or quasar that's sitting at a number of positions. And depending on where that's sitting with respect to the caustic, you might end up with a strongly magnified feature like an arc, maybe a multiply lens quasar, or something in between like an Einstein ring and an arc. So basically, the magnification of the image that you see in the image plane will depend on the location of that background image with respect to the foreground image. The reason we're interested in these objects is basically a number of reasons. So first, it magnifies high redshift galaxies. The background galaxy is probably something that you would not be able to very clearly image if you were just only looking at that background galaxy in and of itself. So when you have a highly magnified arc, you're able to start to really magnify substructures such as the clumpiness of that galaxy and otherwise. Second, lensing is very useful if you want to start to do mass reconstruction of the underlying dark matter. It's very difficult to connect what the underlying dark matter distribution of the system is based solely on the baryonic properties sitting within it. But if you have something that's deflected due to the underlying mass, you can start to make some really nice constraints. And in fact, I think we're going to have a really nice program next Wednesday by Chue on some mass reconstruction as well. And finally, having a collection of these objects, it gives you some sort of a probe into dark energy because the relative position and the frequency of the positioning of your foreground and background object, and also if you have a background quasar, you can start to do some time delay constraints, which starts to probe the geometry of our universe, giving us an additional probe to dark energy that's complementary to the other probes that we now use as well. So the mock data that we use here basically comprises of sort of 4 layers. First, we have source galaxy images, so these are things sitting in the back whose light will get deflected, and those we get from cosmos galaxies that we basically run through a ray tracing algorithm. We have some galaxies along the line of sight, which we extract from the Hubble Ultra Deep Field. We have a lens galaxy, which we model using a singular isothermal ellipsoid and light following mass with a surface profile. And finally, we have on top of that the noise and point spread function according to the telescope, which we would like to imitate. So from this, we have a series of mock observations. The first of which I will show is basically HST, which is the maybe as ideal as you can get in terms of both resolution and seeing, right? It's in space, so you don't have any atmosphere in your way. Next, we have some mock LSST images where we assume we're seeing what we stack over the 10 years, and this basically maximizes signal to noise, but has not great resolution. Next, we basically have a single exposure of LSST, assuming best seeing. So we're here maximizing resolution, but not great signal to noise. So this kind of maybe brackets the quality of data you might expect from LSST insights. So the pipeline itself that we feed our data through can be described using this flowchart. I have like 3 other flowcharts, I apologize if you hate flowcharts. But this is the basic flowchart guideline to what a standard supervised classification algorithm might do. And it starts with a training set where you feed in a bunch of labels and the actual images. You'll want to extract some sort of a feature, feed those features into a machine learning algorithm, which you then use to train and save a classifier model. And then you move on to the prediction phase of it, where you'll now push through a different data set, extract the same exact features in the same exact manner, and hopefully be able to accurately predict the label that you know to be true. So these are all mock data, so we know what the labels are. So the feature extraction method that we use is an edge detection. So the reason we use an edge detection method, I'm just going to sort of illustrate with a cartoon example here. But you can think of the orientation of gradients in an image of a strong lensing system to be able to characterize the arc edges. So this is a sample HST image that I showed you before, and you can see the arcs nicely laid out here. So if you go radially from the center outward of the image, you'll notice that these 2 lines cross some sharp gradients. However, if you go tangential to the arcs, you have a much more minimal gradient going in those directions. Now these are if you're basically calculating gradients through the arcs. Now if you look at the central image, the image of the lensing galaxy, you'll notice that you have sharp gradients in every direction, regardless of what degree orientation you have. And that will also be true of line of sight galaxies. So this is the reason we choose oriented edges as a way to characterize our gradients. In particular, what we use is known as the histogram of oriented gradients, and this is basically a computer vision method used to detect humans for, say, you have a security system and you want to be able to automatically detect if you have an intruder. So basically what we do is we compute a gradient vector for each pixel in our entire image. And within regions, we basically just bin the gradients within that region and create concatenated histograms. Now these histograms now become our n-dimensional feature vectors. The features that we've extracted are these gradients. And there are as many features as there are bins times the number of regions we're binning. So once we have this feature vector, the next job that we have is to be able to now train a model classifier to recognize features that belong to a strong lensing image versus not a strong lensing image. So if I just take the 2-dimensional example, because I cannot visualize very easily in ND, let's say I have 2 of those histogram bins, x1 and x2. Let's say I have a bunch of the features from the strong lensed image sitting mostly on one side and of the non-lensed image mostly on the other side. We use logistic regression, a classical machine learning algorithm, to basically draw a decision boundary between the 2 sets of data points. And basically this linear classifier draws a hyperplane boundary when you extend this out to n dimensions. Sort of a 2D example of what you'll want to now visualize and extend out to ND. So the key thing when you're doing machine learning is you want to prevent from overfitting, right? Because this is basically like an n-dimensional hyperfitting algorithm. And everyone knows what underfitting, just right fitting, and overfitting looks like if you're just trying to fit some sort of a curve to a bunch of points, right? If you have a series of points and you're underfitting, basically the polynomial is too low, something that's just right, somewhere in the middle. Overfitting, you can go through every single point, but the reason you know you're overfitting is because if you come in with cross-validating with a completely independent test data set, the goodness of fit of the new data points is not going to match that of what you fit to, whereas in the just right case, they're going to be comparable. You do the exact same thing in machine learning, except where model complexity is determined by basically the degree of polynomial line fitting, it's going to be something else in your machine learning algorithm. So just to give you a picture of what that looks like, you're going to have some metric for model performance as a function of model complexity. And you're basically going to train a model as a function of model complexity, see how your training data performs with that, and compare that to how well your model performs with your test data, which is an independent data set that you split off. So the way you determine where the optimal model complexity is again to just basically look at where the test data works best. So once we have that, we can use the trained model to now rank order the test sample. So here's something that you probably by eye get a relatively high score of, say 99%. You can clearly see these giant arcs on either side of the lensing galaxy. Something that's a mid-score looks a little something like that, and this was given 40% score. Can anyone tell me whether they think this is a, raise your hand if you think this is in fact a strong lensing system. Raise your hand if you think this is not a strong lensing system, is one of the negatives. Okay, so this is actually, this is in fact a strong lensing system. There's like a very faint, strong arc sort of in the corner there that's probably difficult to see by eye. But at least what you can see it here is like the machine learning algorithm did not confuse a line of sight galaxy for an arc, and certainly didn't do better than this audience if I were to do a percentage of like how many thought it was yes an arc, no an arc, when it decided to give it a mid-score of 40%. And finally, here's a low-scoring image of 5%. So once we've rank ordered our test set based on the trained model, what we can do is now we can use that to assess the model performance. So let's say we've ranked ordered our data, and let's say we actually have a useless model. That's the equivalent of a coin flip. So you collate all of your yes lens, no lens, and basically they essentially alternate. Your model classifier is equally likely to give a high score to a yes lens as it is to a no lens. So the way we quantify how well that model does is we, as a function of classification threshold, measure what the true positive rate, so basically how many true positives are sitting above that classification threshold, as a function of the false positive rate. So the number of negatives that are above that divided by the total number of negatives. So as your threshold marches down, more or less, you're basically just creating this diagonal line across this axis, where you'll notice that the area under that curve is basically 50%. 50% corresponds to a coin flip classifier. Now, what if we were to have an ideal model where all of your true positives are sitting all the way at the top and the negatives all the way at the bottom? That's as ideal as it gets, right? So essentially, your true positive rate shoots up to 1 the second you start marching down. And once you hit the negatives, it marches straight across along the false positive rate. And the area under that curve is 100%. But in reality, with actual models and actual data, you're probably going to get something that's a little bit more like that. And as I mentioned before, this is as a function of classification threshold. So your true positive rate in classification and your false positive rate in classification will depend on the threshold that you choose given this area under the curve. So a strict threshold would correspond to something around here where you're saying, I really don't want that many false positives. Lenient threshold over here, where you're okay with more false positives so you can get more true positives. And a centrist threshold would be somewhere around the mean of this, in the middle. So this curve is typically what's used in the overall field of machine learning to actually assess how well a model classifier is doing. And it's known as the receiver operating characteristic curve, and you can assess how well it's doing based off of the area under that curve. So what we do is we determine optimal model complexity from the ROC curve, namely the area under the ROC curve. So this is actual data now from the mock images that we classified. So here I'm plotting that area under the curve as a function of with a logistic regression coefficient. So it's just basically one parameter that determines how complex the model is, with model complexity going from left to right. So what we can see here is that, training data set, as well as the test data set, pretty much continually increase with increasing model complexity, but kind of taper off after a while. So we basically choose a model complexity where it starts to taper off. Because basically, as you increase the model complexity, the amount of training time will also increase. You also want to optimize for that. You'll notice that this has a different shape from the cartoon I showed you before, and this does in fact go down further, all the way up to the right, but again, because the training time just continually increases, I don't continue out that part. So the resulting model performance with the mock HST basically yields area under the curves of about 0.9. So you'll notice that there's both a solid line and a dotted line to this ROC curve. And the dotted line corresponds to images tested, or trained and tested, where that lensing central galaxy has been removed. So let me talk through why we might do this. So the HST, the thing that just actually performed fairly well, is probably as good as it's going to get in terms of resolution and seeing. Just to remind you, this is what the stacked LSST with worst seeing looks like, and this is what the single exposure for best seeing looks like for LSST. So this case, right, that's pretty bad resolution. You can imagine that if you had a very thin arc right here, it's going to be very difficult to pick out the edges associated with that arc when you have this poor resolution and you have light from the central lens galaxy bleeding over into the arc. So a lot of people, there's sort of a sub-industry where people have started to be interested in perfectly modeling out that central lens galaxy to see if they can actually enhance the features corresponding to the arcs. So we do that test to see how well it does. So again, this is the HST. This is the LSST stacked with worst seeing, solid with the lens and galaxy dashed without. And here's how well it does with the LSST for the best seeing single exposure. Someone told me what's funny about this data. Weird about the results where relating the solid and the dashed line. It's reversed. Right. So when I first saw this, I thought there was a bug. And I was like, oh, great, okay, let me just look through my scripts and make sure I'm getting the right data sets. But it turns out this is not a bug and something kind of counterintuitive. So these results are shown basically trained on 8,000 lensing images and 8,000 non-lensing images tested on 2,000. So it's an 80-20 split. When I first started doing tests, I did it in a smaller subset just to see how things were going. And it wasn't flipped. So that's why I thought there was a bug. So then I decided to basically see how the performance behaved as a function of training data size sets, since that was the only time I saw a difference. Well, it turns out that if I look at just focusing on the blue curves, so LSST stacked as a function of the size of the training set, looking at how well the model does, and compare that to when the lens is removed, you'll notice that when I include the lens and galaxy, there's continual steady increase in performance. But with the lens removed, it kind of just tapers off and doesn't really do much better. And the same pretty much happens for the LSST single exposure. And what we realized from this is that actually that central lensing galaxy adds to the model complexity. It adds to the useful information that allows you to tell a model classifier, is this an arc or is this not an arc? So with increasing data set size, you're able to now describe a wider range of features, a wider range of complexities that can now increase model complexity and take into account the effects of the central lensing galaxy. So lensing galaxies that are much more massive tend to have larger cross-sections for lensing. So basically, the larger the lensing galaxy, the more likely you are to, say, have an image that might be more highly magnified. And what we found is that highly magnified images have higher scores when evaluated by the model classifier. So here I'm plotting the score as a function for magnification for the HST example set. So you'll notice for magnifications less than 5, it really does scatter up and down with some concentration towards the higher scores. But towards higher magnification, say 5 and up, you start to do a lot better. So the higher magnification, which is true also when you're identifying lenses by eye, the easier it is to classify lenses. Now this model performance for train versus test is only from mock data, and a handful of you are probably already wondering, well, it's not mock data that we care about, it's observed data. So what if your mock data doesn't completely represent your observed data? Well, that's very much likely going to be the case, right? Your mock HST data set is probably not going to perfectly represent your observed HST data set or whatever other observations you might want to make, because to tell the truth, right, you probably don't have a complete handle on the exact distribution of, say, lens redshifts and the source redshifts, nor do we have an exact distribution of, say, I don't know, the relative color and age, etc., all of the parameters that go into a lensing model. And in addition to that, well, okay, so maybe we can create a sufficient number of training samples to train on mock data. Let's say we can get it as good as something that's observed with a single type of instrument. Well, what if we want to extend that to another instrument? How can we bridge the gap between those two as well when it's maybe new data that we don't really have very many labels for? Well, one possibility that I think that the field's probably going to start going in is what's known as generative adversarial networks. That's a lot of words, but basically think of this as a machine learning algorithm that can generate data that basically forces that data to look similar to something else. So you may probably recognize this image here. It's like Van Gogh's Starry Night. And this is an image rendered from sort of like an actual photograph that's now been recreated by a generative adversarial network to look as similar as possible to Van Gogh's Starry Night. So it's a Van Gogh rendition of a photograph. Generative adversarial networks have, for the first time, been used in astronomy in a recent paper by Camille at ETH Zurich, where instead of creating art-like images, he basically took some original images of observations, artificially degraded it, and basically trained a network to be able to recover more realistic looking images from the degraded image. So there are a few features in here. Basically, what is done is that the degraded image is fed into a generator that is meant to learn how to generate a more recovered looking image. But it gets that information from a discriminator which learns the difference between the original image and, say, the degraded image. And then it basically optimizes the generator such that the discriminator is no longer able to tell the difference between the two. So here's what it might look like for bridging the gap between an observed image and a mock image. So you're an observed image, mock image, generator, still looks like a mock image. So the discriminator is basically going to know one's real, one's mock. You feed that information back into the generator, and the generator slowly changes with each step. Eventually, you want to sort of minimize the bias. We're thinking of minimizing the bias between what might be going on in mock image versus an observed image, such that eventually when you feed in the output of the generator to the discriminator, it's going to think that both are real. So I do want to be clear, what I'm saying here is you're not going to get more information out of what you're putting in, right? You're basically learning the differences between something that you want to be able to recognize and something that you actually have a large data set of. And it's basically sort of like a pixel by pixel regression to minimize those differences in what you're outputting. So that's sort of a future looks thing that I think people are going to start doing in terms of learning how to classify actual observed strong lenses. So just to leave you some concluding remarks, machine learning techniques will probably be rather advantageous in forthcoming data sets, particularly LSST and Euclid. In this talk, I presented a mock data set and a simple generalizable lensing image classifier pipeline. With a simple pipeline, we've been able to learn something relatively new, that modeling out the lensing galaxy actually removes useful information that can then be used to overall characterize these lensing systems. And I've given you one example of some future steps that the community might take with deep learning. Thank you.
This is great. So hopefully we'll apply it soon to DS, which is also a big data set, which is lots of lenses. But I wanted to ask, I'm still a little confused about how you're doing this in detail. So you've got this feature step where you're looking for gradients in the image, but there's also there's lots of things in lens images aside from just, there's colors of galaxies, there's placement, there's numbers of images. So is that being removed, or is that implicitly there if you have large enough training? So I'm trying to figure out if you're sort of focusing in on certain numbers, certain features, or if you can let the thing sort of decide the feature it wants to look at itself.
Sure, yeah, absolutely, great question. So, right, so we do include, say, the galaxies along the line of sight, right? And when the machine learning algorithm decides which features are more or less important, if you have a bunch of galaxies along the line of sight that are going to have in various parts that's not central, various parts of the image that are sort of somewhat grounded, you're going to get edges in every direction within that region. So it's going to learn that that is not associated with an arc, or with a strong lensing image altogether. If you have something like a perfectly aligned, say like disk edge on galaxy that sort of has the inclination and the relative angle to the central galaxy that's similar to an arc, that's where it's going to get confused. I sort of skipped a middle step between sort of the simple image classifier and the generative adversarial networks, which is just deep learning algorithms, which operates fairly well directly in the image space, and might be able to pick out some more subtle features that are not just edge related from your strong lensing images as well. So that will start to get some of the more nuanced features that we can't assign to the images. But in terms of edges themselves, that's something that the classifier sort of figures out which types of edges and what orientation, what parts of the image are important.
Great talk. Just to follow up on Josh's question, so for example, in your algorithm, the arcs presumably have to be the same color if they're from the same galaxy source.
Oh, sure, like if you have multiple, right, absolutely.
So is that something that's automatically done, or is that something that you kind of have to specify? Does that come out?
Oh, so the algorithm that we're using, these are all like monochromatic images that we have in the blocks. We did test this on a data set put out by the Bologna strong lensing group, where they had kids four-band data. And what we essentially did for that was we created a histogram of origin gradients for each of the four-band images and concatenated those. And that did a lot better because there's sort of inherent color coincidence, I guess, inherent in the edges that have been detected in that. So that's something that for edge detection you'll definitely have to explicitly do. But for something like a deep learning algorithm that would also take into account color in addition to just pixel intensity, that'll be sort of folded in a more nonlinear, complex way.
So I was wondering where the term adversarial comes from. Do people use these to try to trick machine learning algorithms, or?
Yeah, that's exactly what's going on. You want to be able to trick the discriminator into thinking that both, okay, this is actually a real image, but you'd imagine the generator making this look as close as possible to that, such that the discriminator cannot tell the difference between something that's been generated from the mock and something that's true. So there's absolutely a tricking component to it.
It wasn't clear to me, so what prevents this generator from this? If it's some pixel by pixel, what prevents it from this conversion to exactly the same image? So if you're feeding images, the same image, you might as well to converge to the image.
So you're feeding in lots of observed images, right? So converge to, you're feeding lots of observed images, like as large as you have a sample set for, and then and you're basically feeding in some subset of these, and then you basically, I mean, to a certain extent, the generator might be taking some kind of an average of the sample that you do have, right? But you ideally want it to be able to pick out the things that distinguish the observed from a mock.
There's a different method based on convolutional networks that does the same thing without doing this loop. It just extracts layers from the image that are responsible for the small scale features and then reads them onto, you can apply it and bring them next image, which looked to me much better than what you showed for transfer mango style. So, they're different methods, right?
Yeah.
You can describe it very different. So I think for this, there's more efficient way. Maybe that's what Shavinsky used, but there is a more efficient method for this.
Okay, yeah, I mean, yeah, we should talk more, because it
It doesn't have any.
doesn't have to
extracts,
do that.
it extracts the typical features of the actual image and paints them.
But it would have to know that that's what's different between the two as well.
That's done on a layer, so it
Oh, it's
just
on a
takes
layer.
certain layers of the deep network that are responsible for small scale features like noise and data.
Okay, cool. I'll probably be interested in hearing as well. I just submitted a C draft proposal to start doing these types of things.
So I would imagine you've done a test where you take some subsample of your yield data, use that as the training sample, and then apply it to a larger set of yield data. You know how those-
Right, we have not done that with, so the only thing we do that currently is with the HST locks. We have not done that yet with HST Galaxy letters. So that would be like a subsequent step to that. Like feed that in and see if you can somehow fold in the differences that way as well. Right, yeah.
Any more questions?
So, in other contexts, one of the problems with machine learning is that your training sets often aren't representative of the data that you're trying to classify. And that's certainly the issue we face, say, with photometric redshift. Is that going to be an issue for lens classification, or do we think we'll always have to be able to generate good enough simulated images that won't be a limitation?
Sorry, when you say different, you mean like the distribution?
Yeah, the distribution of properties in your training sample is.
So that's
generally
probably,
differs from
yeah, that's
others.
definitely going to be a problem. At least with this, I did do an initial test where we basically have like idealized test, but you have the constant redshifts for the source galaxy, and then try to see how well that's going to do if you have like, a different distribution, and it just does terribly poorly. So that's definitely likely going to be a source of a problem. But there are ways to sort of, probably with deep learning, where if you can be less sensitive to those differences and start varying the distributions and teach a neural network to say, like, don't care about the distribution and try to do something. So there are ways to deal with that actually in more classical machine learning methods. It's known as sort of the covariant shift problem, where the variables fed into your training set are different from the variables that determine what your test data set will look like. And those do exist for like more linear methods. I think it's still somewhat of an open problem in deep learning, which will probably be what we ultimately want to use for the large classification problem for all the data.
So I have a question about LSST. So how do you go about actually getting images to issue the black classifier? Because the problem is the image of data, right? So you need to know where the galaxies are. You need to know, you can't just extract everything, just like every pixel. So is the strategy to actually run it on every pixel in LSST, or is the strategy that you identify some level of galaxies, different only correct galaxies?
Yeah, I think the initial thing would be to look for, say, like journal multiples that are lightweight lensing potential lenses.
How do you know where exactly it is? You wait into levels.
Probably, yes. But I mean, there's also, like, if there's like overlapping footprints where there are other known, I don't think it would be efficient yet to really do a search in every single pixel of all the stacked images. But maybe somewhere we can speak more to the efficiency of that.
LSST is claiming that they will, LSST is claiming to reduce their images to 30 seconds and reduce catalogs and transmits.
Immediately. So as I,
My
yeah.
colleagues said I reduce the size of data all the time. So the key is you need the actual to know where to focus your brand. So because algorithm is an image, right? And the big thing is how do you actually go from 15 terabytes in height?
Yeah, so you make a catalog.
So they're going to make catalogs every night for galaxies. The same.
I
Okay, so students welcome to stay and ask any questions.